Let's start.
Alright, hey guys. So what we're going to do here today is we're going to show you an example of how you can use this final exam review video extra credit to your benefit. One thing that we really want to see for this review is to have interactions between the presenter and the audience. The audience could ask the presenter question, the presenter could ask the audience question, or any combination, as long as it's creative and you guys can actually interact, because that's actually how you form a better connection with these knowledge. So what Dev, Brandon, and I are going to do today is we're going to do like this oral exam format where they're going to be asking the presenter questions and then the presenters can try to answer it to the best of their ability. That way it's high interaction from both the audience and the presentation leader. Okay, so today I'm going to start with 3D equilibrium system. I know it's a pretty hard topic, but one thing we have to note with 3D equilibrium system is that static conditions still apply. So remember that in a 2D system, we're going to have the sum of forces in the x direction is equal to 0, the sum of forces in the y direction is equal to 0, and then the sum of moments about a point, let's just say point A, is equal to 0. So we are super used to solving this now, right? It's pretty easy. But in a 3D system, we're going to have additional directions. And feel free to interject when you guys have any questions. So 3D equilibrium can have up to 6 equations, and that means 6 unknowns. And one important thing for 3D system is that we can have a lot of different constraints. We can have fixed supports, which states that it must have a reaction force in every direction and reaction for the moment in every direction. So that's a reduction of degree of freedom by 6. We can have roller supports, which would prevent normal forces. And if I add a pin here, there'll be a little bit more of a compound support, and that would actually get rid of, that would actually allow rotation in a certain direction too. I know this is a little bit of a bad drawing, but let's just say this is Z, let's just say this is Y, and this is X. Hopefully that looks a little better. Do you guys have any questions so far?
Yeah.
Oh yeah, could you draw the forces of the roller on the XYZ plane?
Yeah. So if I were to physically draw this on, oops, made a mistake. So this would prevent it in the Y, so let's just call this the reaction force in Y. And it's also going to prevent it from going the Z direction, just call it RZ.
So how come it says 2D? If my logic goes like, okay, it's 2D, you have Fx, Fy. How come you only have one moment, but in the 3D you have 3 moments?
Yeah, so basically when we have a 3D condition, we can have X, Y, and Z moments. If we do the right-hand rule where our thumb points when we curve our fingers, that indicates where it goes. But when we're actually looking at it from a 2D view, let's just say this is pin A, The reason why we can only have one moment is because if we follow the right hand rule and our thumb points out of the page, every motion in that curl is in the plane of this 2D view. For example, if I added a fictitious moment in this 2D view, this would mean that I am pointing my thumb this way and it's going to be curling out of the page. So that means there's out of plane motion and you can no longer make that 3D assumption. And if I try to do so in the last direction, same thing. My fingers will be curling in and out of the page, so that would cause 3D motion and no longer have 2D assumptions be valid.
Okay.
Alright. Any other questions that can try to stomp me with?
Does the roller have any moment on any reaction moment on the body?
It can, depending on how it's set up, actually. So, for example, if we have a roller like this that is rigidly welded, and this is the roller. It actually can have a reaction moment, especially if like a length of this roller is given to you, because this bar will not be able to rigidly, not be able to freely rotate because it's rigidly welded, and the roller doesn't allow for any motion this way either. So in this case, it might be able to support moment. However, we can add like, however, we do show rollers in this case for most of this class because of that, where it's actually that looks 3D enough. Here we can see that we actually add a pin support here. Even you'll see this even in your homework examples and textbook examples, because we're trying to show that this bar is able to tilt in addition to be able to roll. So in that case, in this case, this will not have a reaction moment in this direction. I think direction of my arm, I didn't declare a coordinate system yet. And this one, this will have a reaction moment in that direction. Okay.
So what is the general rule of thumb of how do you know in which direction you have a reaction force or reaction moment versus when you don't? So what is the general like approach you would take?
Yeah, so first what I would do is I would try to identify every type of constraints first. Yes, you will have loads, but the loads don't usually cause the reaction forces. In fact, I think they just don't cause reaction forces. So reaction forces means it's inherent in the system, it's reacting to the load. So you all have to identify how it's being constrained, whether it's roller or fixed. And when that happens, is you'll get all the possible reaction moments and forces possible to be experienced by that joint. Unfortunately, if you just do that, you might find yourself with way too many unknowns for the amount of equation you have. So sometimes you'll have to simplify and reduce the amount of moments and forces that something can experience. One way to do that is if you have a force couple, which goes into another chapter. But we do know that a bearing can often support rotational movement, but it's not ideal. because you can break the bearing, and this goes with hinges as well. However, if you have them in pairs, what's going to happen when you have like a moment caused by an external force P is that we're going to have the reaction forces take over instead. So yes, P will cause a moment. However, as this bar rotates, it's going to hit the second bearing, and that second bearing is going to push upwards way before the first bearing starts generating moment resistance. So by doing this, I've simplified the system's forces significantly. Right now, this would have 2 unknowns. Without it, this will have 4 unknowns because it would have a reaction moment here and a reaction moment here, and that's not really solvable with a 2D system like that.
What if I have 3 bearings instead of 2?
Oh, then it actually becomes statically indeterminate, I believe. Once you have that, you really don't know what any of the reactions are doing. You might be able to get a system with 3 unknowns, but if you actually try to solve it, you might see that they're all dependent on each other instead of having like independent variables. If you ever encounter a case like that, you'll need to use solid mechanics, which is next quarter for most people.
Okay.
Yeah. All right, so let's give the stage to Dev and do the next part.
I need to decide. Okay, so hello everyone. This is the second part of the video that we're doing on the video presentation for everyone. So I'm going to go over friction, and the first thing that we learned in class was friction sort of is tangent to the surface that it is in contact with. So imagine this is like a brick, and then this is the surface that it is in contact with. So friction is gonna work sort of tangent to that direction. This is not imagine it is a straight line. So it's gonna work in that direction, and it opposes impending motion or direction. So say I have a force P that is applied onto the brick, and then friction would sort of oppose that motion. And there are 2 kind of types of friction that might occur. One is maximum static friction, and this acts when the block is not in motion, and its value is, static friction is equal to, friction. So what this basically says is that until, so this is static, and so what this basically says is, is that the friction, the force of friction, the value, is less than or equal to the coefficient of static friction times the normal force. This is the normal force, and this is like sort of the weight. And the meaning of this is that the friction force is going to be equal to the force applied onto the body before it reaches this sort of maximum value, and then at this point the motion is impending, so then it converts into kinetic friction, and kinetic friction is just kinetic times mu kinetic times n. And if we look at the graph of friction, it goes sort of like it drops here. This is the maximum friction force, and that is basically the static friction, and then this is the kinetic friction.
How come the static is higher than the kinetic? Like,
Um,
why does it go up and then it just kind of spikes and then drops down and then stabilizes?
So this happens when motion is impending, so there is more sort of resistance to that impending motion than when the block is already set into motion, and then it's sort of the friction coefficient sort of changes because it's already moving.
Yeah, that would be a little bit out of the content of this course, but sometimes it's nice to know about like why these things occur. Just like it helps with short-term memory.
Yeah.
But yeah, like the explanation for that is if you could draw like the two surface with rough features real quick.
So it's like this, and then you have. Okay, let me use another color. It'll be better.
Yeah.
That's the surface, and then this is like sort of the this is the brick, and then this is the brick, and this is the surface.
Yeah. So and this, for those of you on the video, this is what my oral exam looked like, where we ask you to like draw videos and pictures and stuff. So when this is fully jammed, all of those asperities or those peaks get stuck, right?
Yeah.
What do you think might happen once we start to get it moving? Will they like ever be as jammed as before when it's in motion?
No. So once it starts moving, it won't be as jammed. It's gonna be. It's obviously it's gonna move, kind of try to move over it, and I think that's why the kinetic friction coefficient is lesser than the static.
Exactly.
Coefficient. Yeah.
Yes, exactly. So there's actually less contact. There's the similar amount of contact points, but there's less contact volume.
Yeah, that makes sense.
But that goes into tribology and beyond, undergraduate engineering. Okay, so now I actually have a question. Could you draw a sloped surface with a box on it?
Yeah.
So I know in the pre-quiz example, we had a guy holding a box and we want to squish it as much as possible, right? We learned that no matter how much he squishes, there's not going to be enough, it's not going to increase the coefficient of friction, or is it going to increase the amount of static friction?
Right.
Because it's going to be equal to the weight of the box. Now, is that also true when it's slanted, when it's not going exactly downwards? So, assuming that we're pushing P,
So P is
it's going up from the
forward.
bottom. Yes.
So it's going like that, like that.
Yes.
Okay.
And let's just say it's 1 Newton.
Right.
Yeah. And let's say the coefficient of friction is 0.5 for the two box. And
is this static or kinetic?
let's call it static.
Static. Okay.
Now, and then we also had, I know we usually make students find the weights, but let's just say the normal force is provided to you.
Okay. The
And
normal force is
let's just say is 10.
10. Okay. 10 newtons.
Yes.
Right.
So if this box is not moving due to some other forces, is the friction equal to 1 newtons being pushed, or do you think it's greater because we have the 10 times 0.5?
Oh, so since the static friction is 10 times 0.5, which is 5 newtons, and what we're pushing it is with 1 newton, the static friction would have to be sort of 1 newton because it's not moving, and the static friction kind of has to combat the force that's acting on to the brick.
Yeah, I definitely agree.
Yeah.
And does it matter like the surface area of the box, like how big the box is? What if in real world, like I would imagine if I have a box that it's like 1 meter by 1 meter, let's say the same amount of weight, but then I have a smaller box. Does the surface area matter? What do you
The
think?
surface area of contact.
Yeah.
That's a good question. I think not, because when we're looking at friction, we're looking at the normal force, and then we're looking at the coefficient of friction. So it might change the coefficient, but it's not going to change the normal force if it's
The same
The same,
weight.
yeah.
Okay.
So the coefficient never changes.
never changes.
Yeah,
So if the coefficient never changes, then yeah, it can.
Yeah, and that's actually a unique. It's actually a key characteristic of Coulomb's friction. It does matter for air drag, which is like
Yeah.
air friction.
Yeah.
But for Coulomb's friction, there's like this weird statistical anomaly. Well, not really anomaly, but due to statistics, it's saying that no matter the surface area, the point of contact between two surfaces are roughly the same.
Yeah.
So like the coefficient never changes.
Never changes.
Yeah.
Okay.
Okay.
Yeah. So.
Yeah, that's it.
We're
Yeah.
good.
Okay. Thank you guys.
Thank you.